Okay, in this video, I would like to continue with the plate theories. We have covered one theory so far, which is KL stands for Kirchhoff law of plate theory. If you recall, we got a governing equation for the W, the deflection in the Z direction for that theory. And this is the only unknown that we have for the plate theory. And in terms of that theory, as far as the material line perpendicular to the midplane, initial midplane, remains a line and perpendicular to the deflected midplane. Using those kinematics and constraints, we worked out the strain and stress and discussed the some critical points related to that theory, and we got to the equation as you see here. Now, one important thing about Kirchhoff law of theory, or sometimes referred to as classical theory of plates, or classic theory of plates, is this that this ignores the deflection due to shear. Any shear deformation, and that shear is the transverse shear in the Z direction on the plate, side plates, side surfaces of the plates, is ignored. So basically, this theory overestimates the stiffness and therefore underestimates the deflection, and also assumes that the plate is more rigid than it is actually in practice and in physical world. And therefore also you can look at the dynamics, which was not the focus in this video series, but from a dynamical behavior point of view of the plate, the natural frequencies are also overestimated because it is assumed more rigid. So this is a brief background of what we have so far covered. Now we go and look at another theory, which is sometimes referred to Mindlin theory, but it is actually Mindlin and Reissner theory. And in this theory, we go one order higher. If you like, the KL theory or Kirchhoff law theory is zero order. Mindlin-Reissner is first order. By that, I mean, if you recall the Timoshenko beam theory, Timoshenko theory. In that, we included the result is that they included the shear deformation. So deflection due to deformation is counted in that theory. Basically, Mindlin-Reissner is equivalent to Timoshenko treatment of the beam, but according to the with regards to plates. So in plates, we would like to relax our kinematics assumption such that the result of the strain and stress, when we calculate those, gives us the shear strain and of course the shear stress. Okay, one dimension and say which one is which and when to use which one. Well, in practice, we usually treat the slender plates around 5 to 10% of the in-plane dimension for the thickness. So this in this range, we are good with the Kirchhoff law of theory. But as the H increases, so let's say you have a plate, I don't know, maybe 2 meter by 1.5 meter, for example, and then your H start to increase. The plate becomes thicker and thicker. You reach to a point about 20 to 25, somewhere there, and then you say, oh, okay, this ratio doesn't is not valid anymore. So what should we do? You move to this Mindlin-Reissner theory. And then in that line, if you increase the h while keeping the L, TL is a typical in-plane dimension. Uh, I mean here, could be width, could be length, whichever is the smaller. And then you say, okay, as I increase, as my play get thicker and thicker, what should I do? Well, you go to this theory. And if you increase it, then you need a higher order theory, which is like ready third order or other theories. But if you go along that line, then you will see that the point of having a theory kind of fade away. By that, I mean that you get actually to a three-dimensional body. So the two-dimensionality assumption uh, kind of fades away and becomes irrelevant. So either you have to look into the three-dimensional elasticity or 3D elasticity kind of analysis, or go to some numerical analysis, which is very common these days in engineering, and then use a finite element method or a software to do your calculation to get all of the stresses regardless of the assumption. So you don't make any assumptions anymore. You go to the sources. So why do we have these theories, you may ask? I discussed it in the previous videos, because in many practical cases, this h is very much smaller in this range, and we don't want to go and make the effort and investment to do the full calculation for a very small change in stresses uh, along the depth of the plane. So still they are valid, they are good to use, but as I said, as each h increases, we need higher order theories. But for very large h, these higher order theories also is become kind of meaningless, besides maybe academically and intellectually they are valid and they are good efforts, but in practice we use the modern software engineering tools or um, theory of elasticity in 3D. Okay, so having said that, I will use something that we have already developed, and that is when we have this plate, then we had two rotation, phi x, phi y, and w. So these are so phi x was the rotation about x axis, meaning elastic curve in yz axis, yz plane, sorry. And similarly for this is rotation about y-axis. These are my definition. Be aware that in some text and textbook, they define it rotation of the normal to this plane. So you have a change of sign. So this is if you see the equation that we will get to in terms of sign and composition or arrangement are different from a reference that you may be checking or using, be aware that this definition is very critical. I found it more straightforward to define phi x, rotation about x-axis, and phi y, rotation about y-axis. Therefore, we get elastic curve in xz plane. Okay, so we worked out the mid plane. Maybe I draw a mid plane here for our reference here. Mid plane change the pen color back to black. Midplane, deflection, W, and phi x and phi y are defined here. So a material line along the z-axis deflects or transform to deflects or transforms to, as we discussed before, to phi y minus phi x and 1. If you recall, if you have not seen the video on Kirchhoff law of theory, I would suggest that you watch that before this Mindlin. There are many concepts that we will refer to that, and because of that theory, we have identified these quantities that I'm going to use. So if you recall, in that theory, we said that the midplane stays, a material line perpendicular to the midplane stays perpendicular to the deflected midplane. Here we relax that assumption and say that the material line z direction transfers or deflects to this, but is not necessarily required to stay perpendicular to deflected midplane. This simple assumption, or shall we say relaxation of the perpendicularity assumption, is very critical in kinematics of the plate, as we will see. So basically, we can say that the Mindlin, sometimes I refer it to the first contributor along the discussion, or sometimes MR, as I mentioned here. So in Mindlin, which is the same plate Timoshenko, but obviously thicker, we say that we relax the requirement. So basically, phi x and phi y can have independent values, and they are not required to be perpendicular to the slope of the deflected beam, or the dw dx or dw dy at each location or each material point that we have here. They can have, immediately you will see that then the resulting governing equation will be three coupled partial derivative equation, PDEs, for this plate theory. So very small change in our requirement will bring more complexity, but of course richer in terms of predicting the behavior of the plate. Okay, so this will set up the foundation for our Mindlin plate treatment here. And we take that this is the main, everything else remains the same. The material line remains a line. So again, all the points will transfer in the z direction kind of rigidly, but also they can rotate freely, as we said here. So they don't need to stay perpendicular. Okay, so how do we do this now? Now, okay, so let's do these two. These two are actually very important here. So in this one, maybe I start with the phi y, which is the rotation about, maybe I also define my coordinates here. So to be clear what we are talking about, the midplane, this is my x, this is my y, and this is my z. The center, maybe I draw it better here. Okay. So applying the phi y, which is in the positive direction for y, this is phi y, rotation about phi, and in the positive direction for x, this is phi x. Okay, so let's look at phi y. Phi y obviously will create a elastic curve. It will try to bend the plate in the xz plane, and therefore for a material point that we have, say x, y, and w, we need the, say the rx, I call it, which is the derivative of this. Let's say this is r, uh, the derivative of or the gradient, shall we say, of this vector, which becomes 1, the gradient with respect to x, which becomes 1, 0, and dw dx. So this is the tangent to the elastic curve due to phi y rotation in the plane. Okay, so basically if you have this, you will get, and we are in the xz plane here, this is this tangent. So there. Now at any given x and y and w after deflection, now we want that this material line that we have here, the deflected material line, maybe I also write here deflected material line, we would like to find the angle between this vector and this vector. So obviously the in dot product, if you get the dot product, you will get phi y. The second component is 0, so phi x goes away, and the third component is dw dx. So the cosine of this is the angle that we have between these two. So I will call this comma xz because we are in the xz plane. Okay. Remember that in Kirchhoff law theory, we let this to be perpendicular. We treated the cross product, if you see that. And then if gamma is let 0, then we will recover the relationship that we had for the Kirchhoff law theory, which is phi y is minus dw dx. if they want to be perpendicular, or shall we say the cosine of 90 becomes 0, right? So if cosine 90 is 0, then this relationship will recover the Kirchhoff law. But this is what we have. In principle, what we are looking for here is any loss of perpendicularity. So in the midplane, the material line is perpendicular, midplane changes, and then perpendicularity is not required. The plane may be, the midplane material may be in different orientation, which is not required to be perpendicular. That is that angle. Okay, so similarly, for an R, so we calculate here dRy, which is dr, the same r, dy, and this becomes 0, 1, and dw dy. And again, the dot product of this vector and my material line, the dot product, maybe I write it here, the dot product of phi y minus phi x and 1 transpose, and 0 and 1 dw dy gives me both. Gives me the first phi y goes away because this is 0. This becomes minus phi x plus dw dy. Because I am in yz plane, this becomes gamma yz. Okay, so let's put equal here and get rid of equal here. And then these two relationships are key in Mindlin plate theory. Key relationships. So what we are saying here that again, if this angle becomes 90, therefore the cosine 90 is 0, this gamma goes away, and then we recover our Kirchhoff law theory, which requires that the mid plane is always perpendicular to the initially perpendicular material. Okay, so once you understand this and absorb this, the rest is similar to what we have done before. As a summary, we have the same phi x, phi y, w, but we relax the requirement of a material line remains material to the deflected midplane, and then we get these simply relationship. In many textbooks, they come to this based on some sketch-based analysis. I find this vector analysis, if you like, much straightforward and much more rigorous. How did I get this? How did I get this? So for that, I refer you to the Kirchhoff plate theory videos, and the treatment that I had there. I explained that in that video. How do we get this material line after two active rotations? So I will not repeat it here, but it is in the package. If you would like to know how did I get this deflected material line, this vector. Well, maybe I should put a transpose here also to be vectorially correct in terms of notation, but that's fine. The answer is the same. I should also mention that the assumptions of small deflection and small rotation still applies. So these angles are small. The tangent or the slope at the deflected midplane is small. So that assumption is still there. So we are not talking about large deformation, at least in this video. So having said that, for small rotations or deflection, shall we say, can use linear relationship between strain tensor and the displacement. But what is the displacement? Ui is actually, before work it out, z phi y minus z phi x and w, but sorry, and w, but wx is a function of x and y. These are function of x, y, and z, the form that we have here, linear function of z, but phi y and phi x is in general function of x and y, but w, the displacement in the z direction, is function of x and y only still. Why do we get this? Because if you look at here, the deflected beam, if you have a small angle, let's say here, this z times this phi in general, phi x or phi y, this becomes your displacement. And then you get for the v, there is a minus here, so it becomes minus phi x, and w is w. So we discussed again these displacement in the previous videos extensively. But then when you have this, then you can write your Eij easily as d phi y dx z d phi y dy minus d phi x dx divided by 2, and then the third one, phi y plus dw dx divided by 2. And then symmetry means this element of the strain tensor, which is Eyx, is equal to Exy here, and Eyy is minus z d phi x dy, and Eyz is minus phi x plus dw dy divided by 2. And symmetry, and 0, because w is not a function of z. So these I and j goes from 1 to 2 to 3. So for example, if you want this one, E33 or EZZ, becomes E33, so becomes dw dz 2 times goes away, but doesn't matter, but dw dz is 0 because w is 0. So this is our, let me label this. This is Mindlin plate strain tensor. Let's box it. So very important results already shows up, and these are these two quantities here. They are not 0. They are 0 if the bracket is 0, which is the Kirchhoff law of theory. if you assume Kirchhoff law theory, the perpendicularity of material line to midplane is conserved, then these two brackets goes to 0, and then you got 0. So that's why we say that in Kirchhoff law theory, we ignore, or not ignore, actually the kinematic assumption that we, or constraint that we put on the plate gives us 0 shear stress. But once you relax it and get these gammas, which are the shear strain, actually, basically you can say that in general, gamma is 2e. Gamma ij is 2ij in general. These are shear strain, but in this relationship, kind of relate. But this is the full strain tensor. They are not 0. So in other words, what we are saying is this, that if I have my plate, this is my EX, this is my EXY, and this is my EXZ. So this is my EXY. This is my EXY here. This is okay. This is my EXZ. This is my EXZ, and this is not 0 anymore in Mindlin. Similarly, this is my the XZ is non-zero, and this is EYZ. So in terms of surface perpendicular to the y direction, this is EY. This is also EXY or EYX, which is symmetric, and this is EYZ. So this is also non-zero. So this theory gives us recovers this shear or transverse shear strain. But another one that pay attention, and we will come back to it after calculating the stresses, is that this is still 0, the EZZ. Meaning that there is no strain perpendicular to the plane, to the Z axis. So EZZ is 0. So we have to still consider this modified to the plane strain or plane stress assumption by integrating over the Z. So these are the properties that we have, or we can extract from the strain. Let's go to the stresses. Now, the same discussion that we had in Kirchhoff law of theory, and I summarize it here, but for full discussion, please refer to that series, is this, that if you go after a 3D elasticity constitutive relation, or shall we say 3D Hooke's law, relating stresses to strain, and I calculate the stresses, you will run into issues for satisfying boundary conditions or surface traction compatibility, and so on and so forth. Also, we have some indication here that there is some sort of two-dimensionality still for this theory. And actually, this is the beauty of these theories that turns 3D to 2D for us. So we have to use the modified average, the basically 3D Hooke's law in order to calculate the strain tensor. We will do that by applying the stress strain relationship, and I will use the previous discussion that we had here. So these are 3D. We don't want to use them in this way, but we want to basically uh, integrate them along the z-axis and then use them. Now, these are the equations that I'm talking about. So constitutive equations. So if I let's copy and paste here. To save some time. Okay. Okay, sometimes these software takes some time to react. Okay, so what we have here is a 2D Hooke's law, and then for that we have this we have the sigma x, sigma y, and tau or sigma xy written here in terms of the modulus of elasticity and Poisson ratio. So E is sorry about that. My notes stop responding. So, but E is the modulus of elasticity, mu is the Poisson ratio, and tau xy is the same as sigma xy, change of notation. Sometimes we use tau for shear, and G is shear modulus of elasticity. So we have these Hooke's law here, two-dimensional. I put plane stress in quote unquote because it is actually the modified or special case of plane stress that we will look at when we go to equilibrium equation. So now if you come and substitute for strains into these equations, then you get the stress. And your sigma ij will be shall we say Ez divided by 1 minus mu square d phi y dx minus mu d phi x dy. This is sigma xx. Sigma xy is Ez divided by 2 1 plus mu d phi y dy minus d phi x dx, and the shear is E divided by 2 1 plus mu multiplied by dw dx plus 5y. Here we have symmetry, meaning sigma yx is equal to sigma xy. Sigma yy becomes ze 1 minus mu square d phi x dy plus d phi y dx. And the shear on the surface perpendicular to the y-axis becomes E divided by 2, 1 plus mu multiplied by dw dy minus 5x. Again, symmetry. Now, this sigma zz also becomes 0. So let's 0. And this is sigma zz because your ezz is 0. Okay, so immediately we see some issues here again, and that is, so we have recovered the in-plane shears as I mentioned here, as I sketched it here, but sorry, the transverse shear, but we get some issues with the normal stresses on this plane. Why is this issue? Because if you have a traction applied on any surfaces of the plate, then this says that it is 0. So we have to kind of do some recovery for these things. If you recall or if you have watched the video for Kirchhoff law theory, and again I highly recommend that you do that before Mindling, we didn't have these two in-plane stresses or transverse, shall we say, in stresses. But now we have it, but still we have the normal stress 0. And this 0 is not an assumption. It's very important to realize that this 0 is not an assumption. It is the consequence of the kinematics assumption that we have. All of the assumptions that we have for this Mindlin, especially this one, this is the consequence of that. Okay. Now, there is some manipulation here that I will write it and then explain it as we go forward to save some time. And this is the same as treatment that we had. One thing is here that when we have these stresses, and maybe I draw this and explain here also, similar to what we had for this the normal stress sigma x and sigma xy and sigma xz, and similarly on the y plane. So these stresses are responsible for some this is responsible for creating moment. This is responsible for creating twist, and this is our transverse shear. So what we do here, we will not go after each one, but we will go after a quantities, or we call it integrated quantities, that we will calculate based on the unit length in the direction that we are calculating, and then use those in order to find our equilibrium equations. Okay, continuing, I wrote these things down to save some time, but I will go through it explaining. So what we do, we will come and integrate the stresses along the Z, the thickness of the plate, minus h over 2 to plus h over 2, meaning from top to bottom because our Z is in the downward direction, Z axis, and multiply it by Z and for the normal stresses, uh, and similarly for Z sigma Y. I use one index for the normal. So this is sigma x or sigma xx, if you like, sigma y or sigma yy, and sigma z or sigma zz. So these two are calculated with the same limit of the integral. And for the in-plane shear, which is sigma xy, I use the same multiplied by the z. And so why multiplying by the z? There is a very important and point to pay attention to. If you look at these stress, for example, sigma x, everything except z obviously is a function of x and y. So basically, we can say that this stress is a linear function of z at any given x and y location. So it will varies linearly along the depth. Similarly for this component, and when you come to the shear, in plane shear, sigma xy, for example, it is constant. It is not function of z. So that means that this stress will not vary along the depth. It's a constant. And that creates another issue. That's why we need to go to higher order theory, kind of it dictates us to go to higher order. Why? Because if this shear is constant, this shear, this sigma x, which is this one, is constant, and we don't have any shear on the surface top and bottom, then we run into compatibility or of the shear. We cannot have a shear on this surface without having a shear on the perpendicular surface. So in other words, yes, there is a shear here, but the value at the intersection of the that plane, let's say this normal to the x and the top surface normal to the z, the shear stress should be zero, the transverse shear. Similarly for this one on this side. So obviously this cannot be constant. There is a remedy here similar to what we have done for Timoshenko, and we define a k factor. For beams, they call it Timoshenko K. Here we call it maybe Mindlin K factor to recover that. But pay attention to the variation of these things. So once we have that, we multiply by this to get the moment. That's why we call it M. So this is the moment as a result of normal stress. This is the moment as a result of normal stress in y direction. But this one is a twist because this is in plane and varies linearly. Then this will try to twist. It's a moment in the direction of the x, and similarly for y, because sigma xy and yx are the same. They try to twist the plate as a result of these moments. Now for the shear, we do the same, and that is integrating the sigma xz and sigma x. Actually, this should be sigma, let's see here, uh, it should be sigma yz. Yeah. So this is the transverse shear here, and the transverse shear, this is sigma y, and this is sigma yz. and these two are the same, sigma yx and xy. Okay, so sigma yx. Now we will during the integration, we collect the constants, and there is an integration of, because this here you get a z square, because if you go back here we have a z in each component of these stresses and multiply, so we get the integral of z square over z square along the depth, and that gives you some constants. So we connect all of those constants and put it into a constant, we call it d. Traditionally this is called d, and then you come and put the stress elements, these elements, which are again function of x and y. So this integral is not very scary, because all of these, let me, maybe for this one I mark it, all of, except z is a function of x and y. So for example, here this comes out of the integral, and you have a simple integration to do. But there are few of them that you have to do, and if you do that, you get these equations. So for mx, this would be my relationship uh, based on the phi y and phi x and w for the q x and q y. So what we have done here is basically not directly using uh, the stresses, but the resultant of them, or the quantity resulted from these stresses, of course per unit length, because we are assuming a per unit length. You need the area to get the force times the arm of that force to get the moment. But here is dz multiplied by 1, basically, which is in the direction, for this one is in direction of y, for this one is in the direction of x. Okay, the k factor, as I mentioned here, because the actual shear stress varies along the thickness, uh, and here we discussed that the shear stress according to this theory is constant, so we have to introduce a k factor, and then that is introduced into the coefficient for the qx and qy, uh, and I collected all of them under s. So our qx and qy equation will be modified to, as given here, s multiplied by the bracket and qy s multiplied by this bracket. Now, because of the result of our kinematics assumption that we got strain in the z direction 0, and also the stress in the z direction 0, we have to come here and do a average equilibrium equation. If you recall, the three-dimensional elasticity for equilibrium, which is the equation that the stresses that we calculated should satisfy this equilibrium. These stresses are based on some assumptions. So now this is the catch. So these stresses should satisfy this equation. And chi is a body force. So if we let chi to be 0, then we get these three-dimensional elasticity equations. Now we come here and average them, meaning integrate these equations along the z after multiplying by the first two by z and integrate it, and the third one just integrate, and then we can use the mx and my and etc. that we already calculated. So if you substitute into these average equation, you will get an equation like this. So if you like, this is our uh, equilibrium equation in terms of M and Q. This Q, the lowercase q, is the pressure, or shall we say the load which is applied on, say, one side of the surface, one side of the plate, the surface usually at the top, and this is the force per unit area. So it's a kind of stress in the negative z direction. So it will show up here. So that is your Q. It could have any form. It could be constant. It could be any form that you want, but it's a distributed load on the top surface. Now, after, if you come here and substitute the mx and my and all of them that we calculated here and do some manipulation, you will get these equations. These are the celebrated Mindlin equations. Governing equations. So as you see here, we have a system of three partial differential equation that it is coupled, and then if we want to get the answer for w and phi x and phi y, these are our three unknowns, and these are the equations. I collected here the d. Some constants appear during the manipulation. The d appears here, is given here, and the s is given here. And you see the k. K is usually, k is typically 5/6 for a, depends on the shape of the plate. Usually it is rectangular, and then we get it 5/6 typically, roughly. So the K is tabulated for different shapes, but as I say, for a plate, if we get a cross section of the plate, it is a rectangle, so we get 5/6. So this is the Mindlin. However, it can be shown. It's a lengthy derivations, but I will not go through it here. It is a lengthy derivation that it can be shown that we can derive a single equation for W. Basically, you do some manipulation here, and then you eliminate phi x, phi y, and then you keep W, which is the deflection in the z direction, and that equation is interesting, and that is given as by harmonic on W, del 4 is equal to Q, the same Q, over D, the same D, minus 2, 1 plus mu divided by E, KH, Laplacian of Q. So this is Mindlin, no assumption, just manipulation. Mindlin equation for W. As you see here, we have a biharmonic, and biharmonic is the Laplacian of Laplacian, and that is d4 dx4 plus 2 d2 dx2 dy2 plus d4 dy4. The operator. So shall we say where? And Laplacian, no. Now there are several things here that I would like to point out before closing this video, which is already 1 hour, although I try to save some time, uh, that is that this quantity here is actually, if you work it out, this quantity, note 2 1 plus mu over EKH is actually 1 over S. This S is actually shear rigidity, or if you like, shear stiffness. Rigidity. So what we are saying here, that if S goes to infinity, this quantity goes to 0, means the plate is rigid for transverse shear. And so this last term will be 0 because this coefficient is 0. And then you recover the Kirchhoff law of plate theory beautifully. And this is exactly the difference between these two plates. So we assume rigid shear deformation. So I hope this package, all of the videos, help you to understand plate theories and why we have plate theories. I cover two plate theories here, which are heavily used in practice. Kirchhoff law, sometimes it is called also technical plate theory, and the Mindlin-Reissner, sometimes referred to as simply Mindlin, in practice. And one ignores shear deformation, the other one, the second one, Mindlin, includes the shear deformation and the resulting equation as we discussed. Thank you very much.